Okay, folks. So in secondary structure, I want us to remember that we're really focusing in on what's happening to the backbone of the protein. We're going to kind of ignore the R groups. We'll know where they are. We'll know they're there, but we're going to really focus in on the backbone. Some things we have to keep in mind about secondary structure. So we have a peptide bond in peptides. That peptide bond is the bond between the C terminus of one amino acid and the N terminus of the next amino acid. That bond is planar because the carbonyl and nitrogen are sp2 hybridized. That's a throwback from Gen Chem. So this bond is planar. It's important for us to recognize that the nitrogen has a lone pair. And since that nitrogen with a lone pair is directly next to a carbonyl, it can participate in resonance to create this resonance stabilized structure, which is why we say that the nitrogen is also sp2 hybridized in a peptide bond. Because we have this sp2 hybridized peptide bond, we understand that this whole region in the peptide bond is rigid, doesn't rotate, and it's planar. Some of the bonds can rotate, okay? So the bonds on either side of this alpha carbon are able to rotate. They have names, phi and psi. You don't need to memorize that, but it's kind of good to keep in your mind. So those bonds can rotate, creating different angles between the carbon and its bond. Let's zoom out a bit. Okay, so we know that some of these bonds can't rotate and some can. So when we have a peptide, how would we expect the amino acids that are sequential to kind of be relative to each other? Well, the R groups of amino acids in general are going to lie trans to one another due to steric hindrance. So this first R group in white is pointing up, the next one is pointing down, the next one is pointing up, etc. Because that way these bulkier R groups aren't kind of smashing into each other. Let's remember that steric hindrance has to do with whether or not these atoms and their electron clouds are kind of be like bumping up against each other and causing strain. To avoid that strain, boop, 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 just get them going off either sides of this peptide chain. Oops, excuse me. What else should we know about secondary structure? Well, let's dive in a bit deeper and zoom out to what kind of shapes the backbone can make in secondary structure. There are 3 types of secondary structure that I'm going to want you to know for this class, and I'm going to want you to understand how each of the secondary structures are stabilized. We have alpha helices, beta sheets, and turns and loops. The alpha helix occurs where the backbone kind of wraps onto itself, kind of like a DNA helix. You will oftentimes see the alpha helix shown as a cartoon like a ribbon. Now on the bottom right hand side, I've shown you the space filling model just so you can kind of see how an alpha helix looks when all the atoms are visible. What I want you to understand though is how this structure is stabilized. So the carbonyl oxygen of one amino acid performs a hydrogen bonding interaction with the amine nitrogen of the amino acid 4 away from it. Okay, this is what stabilizes an alpha helix. Let's look at the picture on the right-hand side to see what I mean. And let's look at this carbonyl here. So this carbonyl oxygen is performing a hydrogen bonding interaction with the nitrogen, the hydrogen coming off of this nitrogen, 4 amino acids away from it. Let's do some counting. So there's 1 carbonyl carbon. Do 1. There's number 2. There's number 3. And here's number 4. So 2, 3, 4. You can see the hydrogen bonding interaction taking place between this first amino acid that we're counting and the amino group of this 4th amino acid that we're counting. Big takeaway here, folks. The alpha helix shows the backbone of the peptide in this kind of ribbon form, and the ribbon is stabilized by hydrogen bonding interactions between carbonyl oxygen and a hydrogen coming off of a nitrogen. The next type of secondary structure is the beta sheet. So in a beta sheet scenario, we have kind of just strings of the peptide. So rather than the peptide kind of curling in on itself like an alpha helix, it's more flat, more linear. Beta sheets are often represented by ribbons that look flat with little arrows attached to them. So that's often how a beta sheet is represented as a cartoon. Beta sheets are also stabilized through hydrogen bonding, and that's shown on the slide. The hydrogen bonding can occur in a beta sheet that is anti-parallel. What do I mean by anti-parallel? Well, beta sheets generally work in pairs. And if one beta sheet is pointing with its N terminus and C terminus in one direction, and the beta sheet that's doing hydrogen bonding with it is pointing the other direction in terms of its N and C terminus, we'd call that anti-parallel. However, beta sheets are parallel if the N and C termini are pointing in the same direction. Let's start with anti-parallel. In the anti-parallel, you again have hydrogen bonding interactions between a carbonyl oxygen and the hydrogen coming off of a nitrogen. In the anti-parallel scenario, these hydrogen bonds are perfectly aligned, nice and short. In this parallel scenario, you can see that the hydrogen bond is a bit longer, a little bit off at an angle. So this hydrogen bonding interaction is stabilizing for beta sheets. Hydrogen bond is a fairly strong type of interaction, and it's particularly strong in an anti-parallel scenario where the hydrogen bonds are perfectly aligned. The final type of secondary structure, folks, is called a turn or a loop. So a turn or a loop is going to connect portions of alpha helices to each other, or connect portions of beta sheets to each other, or connecting an alpha helix to a beta sheet. You really think of them as these like little spaghetti bits in the cartoon. They always kind of look like these little spaghetti strings, and they're connecting structure to one another. Turns and loops are most often found kind of on the surface of proteins, connecting the other types of secondary structure to each other. And they very often contain the amino acids glycine and proline, and they contain more amino acids, of course, but they do usually contain a glycine or a proline. And let's think real quickly about why this is. Why a glycine or why a proline? So glycine, the R group, is just a hydrogen. When we're thinking, folks, about a turn or a loop, keep in your mind that this turn or loop is physically bending, right? It is physically bending. If we're thinking back to how we can have rotation around the alpha carbon, probably the smaller the R group is, the easier the rotation is going to be. And so that rotation should kind of help the turn and the loop. They also oftentimes contain proline. And so proline, folks, is great for a turn or a loop because the backbone is bent within the structure of proline. Okay? That's probably a little bit confusing. So most amino acids, right, are linear, N-terminus to C-terminus. Proline, on the other hand, has the R group that goes back into the backbone. So the backbone is kind of connected to the R group. This causes a bend in the backbone of the peptide because of the structure of proline. If turns and loops are supposed to do a little bending job to connect these types of secondary structure to each other, we would expect proline to be there since it will help that bend occur just due to the structure of the R group of proline. However, you'll notice I did not talk about hydrogen bonding at all for turns and loops. So we generally think about these as less stable because they do not do hydrogen bonding, unlike alpha helices and beta sheets. Those are the three types of secondary structure.